Hello everybody, we are Luca Fascione and Rob Canel from Weta Digital. Today we're talking to you about implementing PhysLight in a real-time renderer, Gazebo. So what is PhysLight? PhysLight is Weta's method for describing how much light really, moves through a scene, and we do this by talking about lights and cameras in real-world units. PhysLight enables a whole new level of simplicity and control to better realize the director's visions on their show, because it unifies the language and the thinking processes between the two worlds, physical and virtual. The PhysLight process has been in use for at least 5 years at our studio, and you can see in the slide some of the productions we used it on. In the rest of the talk, I'll walk you through what this means in practice as a change in our lighting processes, and then Rob will discuss what had to change in our in-house real-time renderer Gazebo to make it happen. The discussion in this talk is fairly high level because the PhysLight source code is currently available on GitHub, see the URL on the slide, and we contributed a reference implementation to BBRT version 4 as well. Let's start from this frame, taken from the movie War of the Planet of the Apes. As you know, all the apes in this frame are graphics, and in fact this is the frames as we received from a client. You can see that there are actors wearing motion capture equipment on set. Andy Serkis himself, the actor for Caesar, is here visible in the right-hand side of the picture. In order for us to be able to use a shared language, let me quickly recap the steps needed to turn this image into the final frame as we saw it in a moment ago. Naturally, the first ingredient will be a renderer. This will take the scene geometry, the lights, the shaders, the textures, and the camera to produce an image for our digital characters. The next step is then to composite the render image of our characters onto the plate photography to create a final picture. As a side note, much like this is the conceptual process of how the movie is made, we want to be able to see as close as possible an approximation to the final result into our interactive processes as well. And this is where Gazebo comes in. More on this later in the talk. In this picture, you see a flattened out spherical image of the set a few minutes before the frames were shot. We use images like these for environment lighting. We call these IBLs, for image-based lighting. Our photographers on set captures images like this one, as well as reference footage like this. Here you see a stage technician, also on set, holding a cream ball and a gray ball. The balls are used to give us the reference of how the light was flowing on set. These are objects that we can model relatively accurately, and in our whole process they will be a key ingredient for us to be able to calibrate. You can see at the right-hand side of the image, we also have busts of our character available if further tuning should be necessary. Once the shot is turned over from our set, we make images like this. You can see two spheres. One is a render, and the other one is a clone of the one from the footage you saw before. Given that those two spheres don't look the same, in the old process we would adjust the brightness of the IBL to achieve a closer match. Say like this. You can see in the readouts that in reality the average brightness is numerically quite different from the target photography. But if you look at it with the naked eye, the images feels quite closer than the numbers seem to imply. This is because of a number of reasons. First off, the material in the digital sphere is a close approximation to its real-life counterpart, but it's not perfect. And as you can see, this is a rainy day, and so the real-life ball was actually quite wet and a little dirty. And in practice, through many days on set, a grey ball gets occasionally scratched and it ends up needing to be repainted. All this is to say, there was a substantial amount of judgment necessary in the old process to achieve a match that was good enough to make movies with. Let's now look at another aspect of the process, what happens to the background plates. You can see here a group of 9 frames from the ancient shots. Due to a number of technical and practical reasons, the material that gets turned over to us from our clients is often quite varied in look. We could certainly work with the material as we do receive it, but you can imagine it would make it quite a bit harder to make sure that our digital content look right in all these different conditions. So instead, our colorist team applies the incoming plates what's called the neutral grade. Grade is the word that we use when we talk about color correction. When the plate comes in, our colorist team goes over all the material and color corrects it so that it has a consistent and neutral look, sequence by sequence. In this manner, we can be sure that if our RBL lights are appropriate for one of the shots in the sequence, they will work for the other ones as well. As you can imagine, once the graphic is composited into the shot, the look that the client desires is further applied to the images, and the finished frames are delivered back to them. In this particular case, we have applied the client look to the source frame to make the difference a little bit more evident. Okay, so This is the overview of how we used to work. As you can imagine, this is a fairly labor-intensive approach, so we started asking ourselves if a more first-principle method could make our lives simpler and help us resolve at least some of the uncertainties that were involved so far. So we went back to the basics and did an experiment. Here you see a fairly simple setup. We have a chrome ball, a color checker, and a gray ball. We have a couple cameras and we have 2 blondes. This is Simmer's peak for a 2 kilowatt light, as opposed to a red head, which is inside a 1 kilowatt light. This is because the 1 kilowatt lights were introduced by the brand Mold Richardson, and they like to have a red housing. And the 2 kilowatt lights were instead introduced from Strand Lighting, and they prefer to paint their housings yellow. But we're digressing. From this setup, we can make a movie like this. So the question is, can we gather data about the lights and the camera only and use that to make this picture again without any manual adjustment? First thing we need is a language to talk about light sources. There are 2 kinds of light sources. There are lights that are relatively at close distance, we call them area lights, and there are lights that are at a large distance. This we encountered before, these are the IBLs. For nearby lights, we have 3 ways in which the light is distributed. It will vary spatially. Looking into the light, all the sources will have their own shape, if you will. The light will have a spectral distribution. This is how intense the source is at a given wavelength. And the light will also have an angular distribution. This captures how the light folds off for angles that, are far away from the forward direction. Here's a color study that we have done while working on Gemini Man. The character you can see here was called Junior. This is a render of Will Smith when he was in mid-20s. In this picture you can see a few things. One is the effect of spectral versus RGB lighting, which is interesting for our offline rendering through Manuka. But in the bottom left of the picture you can also see an image of the actual shape of the light source. As I change the light, you can see that not only certain spectra are harder to approximate in RGB than others, but also that the shape of the source substantially affects the shape of the shadows in the picture. Here is a third source. Let me flick back and forth one more time. Look at the shadows as they fall on Junior's neck near the middle of his collar. The 3 shadows are substantially different, and this is only due to the shape of the source. So let's go back to our light description. Now that we know what these terms are for, how do we relate these quantities to things that we can actually measure? Actually, this turns out to be fairly easy. First, we normalize away the total contribution of the 3 terms, dividing by the emission constant. You can see a little piece of code here that shows you how to compute it. At this point, we have a light that is unit emission, and we can simply scale it to be as bright as its real-world counterpart. You can see that the brightness is called luminous power and is measured in lumens. You might be surprised it's not measured in watts. This is because the different kind of light sources show fairly different levels of efficiency in turning electrical energy into light. For example, tungsten-based emitters are mostly emitting in the infrared band, where we cannot see. Since household lights have moved to LED technology, packaging for everyday light bulbs also displays the brightness of the lamps in lumens, because that way different bulbs can be compared more easily. Alright, so back to our experiment. We will do one more step. We will pretend that our studio is large enough that capturing an IBL for our setup is actually appropriate. This gives us an opportunity to discuss what to do with the IBL case. Let's look at our blackboard again. So here we go. This is all very similar to what we had before for area lights. There is a brightness for each incoming direction, each pixel on a light image, and there is a similar emission constant to turn our IBL into a unit emitter like we've done before. The code shows you how it's done. But note that IBLs don't have luminous power, they have illuminance, and the unit is lux. This is because whereas lumen measures how much light is leaving a light source, lux measures how much light is arriving at a location. A lighting technician might use an instrument like this one. The little white dome collects light from all the space in front of the sensor. Whereas this one is a handheld light meter that a photographer might use. This is called an incident light meter. This is another model from a different brand. Note that this particular model has both a white dome for incident light measurement as well as an eyepiece to look through. In this second mode, this is called reflected light measurement, a different quantity is acquired which is measured in nits. We do not want nits for this purpose, we need lux. Now let's move to cameras. Now that we know how to measure how much light is being emitted into a scene, all that's left to understand is figuring out what happens when this light arrives to our camera. The camera has 2 separate and fairly important behavioral axes. One axis is response to brightness, and the other one is how the camera responds to different colors, meaning their hues. This is captured in the slide in two parts. On the right-hand side, you have the sensor response. This is how the camera reacts to different wavelengths of light. This is the heart of the camera's color fingerprint. On the left-hand side, you have the imaging ratio. The imaging ratio is this formula that describes how the brightness of the picture is affected by the settings in our camera. The exposure time, the field sensitivity, the aperture number are the important ones. Note that the discussion of units is slightly delicate for this space. In particular, you will notice that for the energy density, the brightness of a single pixel, we have Talbot in double quotes. This is because each one pixel is really capturing either red or green or blue response, whereas true Talbots would be the true brightness of the pixel, the luminance. That's the response of the sensor if the camera was a black and white model. Now I want to go back to our IBLs for one more bit though. We just spent all this time saying how good a camera is at capturing light values, and the IBL is after all just a photo. It seems like we could be a way to use this to our advantage. In fact, it most certainly is. If the shooting parameters of an IBL are known, and they often are because the EXIF tags come from all DSLRs I use these days, we can just invert the camera's imaging ratio and go right back to real-world values as we had at the time of capture, without any need for adjustments. So you can see that either the top or the bottom approach will be quite useful depending on the specific part of the lighting workflow you're in. With all this in place, let's see if it will work in practice. Here's our test from before, and here's the graphics. Note that this image does not use the spectral response in the camera, it only uses the imaging ratio part. And here we're adding the sensor response as well. This brings the color in the color checker much closer. Let me compare again. Just the imaging ratio, sensor response also. Imaging ratio, sensor response. So, what does this mean in practice? Well, we did put this into our processes, and this enabled us to make shots like this. PhysLight really shines in naturalistic scenes. This is a shot from War for the Planet of the Apes. The fortress environment is lit by an IBL captured on location. Due to the large exposure difference between the sky and the torchlight, the outside part that you can see now, and the inside of the fortress you see as soon as the camera pans around, the interior lighting is augmented with hidden fixtures captured from similar lighting setups in real-world set pieces. But the question, of course, that we have is how do we compare to the various torches around? The torches in the interior have their brightness and color derived from torches captured in the IBL in a different scene. This is another example of using cameras as reference light meters, and a fairly accurate one as well. We then tune our fire renders to give us a black body emission that was matching in brightness the colors from these images. Now any shot in the movie with similar torches can be lit digitally with exactly the same thought process that would be employed in the real world, without needing to retune for fire of any single shot. I now hand over to Rob, who will talk about Gazebo and how PhysLight works in a real-time renderer.
Hello everybody, I'm Robert Kennell and I'm the lead engineer on the Gazebo project. And I'll be talking about some of the ways Gazebo is used here at Wedded Digital and what we've done to integrate PhysLight. Gazebo is built as a plugin architecture so that it can be easily integrated into DCC applications. One of the main responsibilities for Gazebo is to provide faster feedback and iteration times to its users. Here we can see Gazebo rendering a Pixar USD scene in Maya. Here we have the same test scene rendering in Gazebo and Maya using Atlas. Atlas is our framework for scene description and allows for the building of higher level tools and services, and conceptually this is similar to USD. There are tools that work within the Atlas space that are responsible for providing data to Gazebo, and here in this example we have Bake providing model data, Light Ninja providing lights, and Lumberjack providing vegetation data. Our plugins provide data to Gazebo via a versioned API, and this gives us clean separation between data and rendering. Plugins don't have the knowledge of how their data will be rendered, and Gazebo knows nothing about the pipeline. Gazebo is used in many departments such as animation, previs, motion capture, and stage, and can exist in many different hosts. And here is an example of the same scene loaded in Motion Builder with Atlas providing scene data. And here we have an example of Gazebo in Katana alongside a native Katana viewport. And this is Gazebo rendering in Houdini. Gazebo can render in 3 flavors: fast, precise, and ray traced, with each mode providing benefits at the cost of rendering performance. We also need to be able to consume hero-level geometry and textures, and this allows Gazebo to adapt to the department's and shot's needs. For an example of how Gazebo can be used in a pipeline, we'll first start with a final shot with crowd and hero animation from Avengers Endgame. Here is the same shot with our cached interactive crowd system. This allows crowd artists to cache out their crowd in 3D for sharing with animation so animators can work with the crowd in the background. This can also be loaded quickly by other departments like layout. And here is the animator's view with keyframe, characters, crowd, and rough lighting. With all of that in mind, here we have a high-level overview of our rendering pipeline. We take in scene data, lights, shaders, textures, and render our CG. Then, plates are composited into the scene, and finally we will apply imaging transforms depending on our output target. Here we have Harley Quinn and Bruce. Obviously it wouldn't be appropriate to shoot scenes like this with Margot Robbie interacting this close with a real hyena. And these are Gazebo barbershop renders composited for the purpose of validating the animation with our clients before final renders are started. And you can see in this shot, a coarse matte outline was used for the hands just to give a sense of relative placement between the performer and the digital creature. Looking back at the pipeline now, we can see that the pipeline can get quite complex, and for us, pre-processing is not always the best option, as our data is often in flux and users require fast feedback. Our plugins therefore provide color space, imaging, and grading settings to Gazebo via our API, which allows Gazebo to convert the inputs into a common working space. Lighting in Gazebo is a mixture of different techniques to allow flexibility in lighting for our users. This can depend on the mode that Gazebo is being used, and it can range from ray tracing to VPLs to real-time image-based lighting. For PhysLight and area lights, we want to extract out information that we can pass to our core lighting pipeline. So, during pre-processing, we calculate a number of values, and the first of those is the emission constant for the area light. If the area light is textured, then we also calculate the average luminance, which will be used to scale the emission constant. And finally, we take a number of light samples on the surface of the light for our VPL lighting. Then we take the emission constant and the sample color, and we use that as the input intensity for our lighting. If the lighting method does not need the sample color, then it is just ignored. Our image-based lights are taken with a known camera so that when they are used in Gazebo, we have all the information we need to convert them to camera RGB space. Once again, we cache the emission constant for this. Next, we calculate the upper hemisphere illuminance, and we also cache sample colors for some of the lighting methods. And finally, the emission constant and light sample colors are used to calculate final lighting as per normal. As mentioned before, the sample colors will be used for VPL and other lighting types, but for our physically based image-based lighting such as environment maps, we don't need to use the sample color. Once we have a final frame, we need to get it into a space that is appropriate for client delivery. At the end of our frame render, we are working in RGB space, and white balance needs to be calculated in camera RGB space. We also need to apply grading to get the look required by the client. The entire transformation from working RGB to delivery RGB works out nicely as it is handled via one transformation matrix. There are a few challenges that can show up, and for us, one of those challenges is with lighting. As we've seen before, there are many types of lights that we need to support, but some DCC applications can also have non-physical lights such as point lights, and we want to support this in a way that does not clutter our rendering pipeline. Here you can see that it can get quite messy quickly, as we have to deal with a mixture of non-phys and phys lights as inputs to our lighting, and we can't just have only phys lights from start to finish like offline rendering does. To solve this, we convert our lights to a common space that is then passed into our lighting calculations. Another challenge is dealing with plates that already have PhysLight imaging applied. If you recall the pipeline overhead diagram from before, you will see that we need to handle this during compositing. And obviously we don't want to double correct these plates. To handle this case, image plate textures have their imaging inverted via an inverse imaging transform if needed. This, combined with our other conversions, will bring the plates into our working RGB space so that they are ready to be composited into the rendered scene. This approach has been battle tested in many shows and we are very happy with the results. Hope you enjoyed, and thanks.